When we talk about the strength of an acid, we're actually talking about how many little free hydrogens are zipping around in the container. If you drop in a compound, an acid, with an H and some sort of negative ion bonded to it, and they're not attracted to each other much. See this weak attraction, this skinny little arrow compared to this stronger arrow? If these guys don't care for each other much, and they're not really trying hard to stay together, when you put it in water, you're going to get lots of these guys, lots and lots and lots of these hydrogens zipping around because they don't really bond much to this over here. If that happens and you have lots of H's zipping around, then it's going to be what we call a strong acid. Over here, there's a very big black arrow representing a huge attraction between the positive and the negative. These guys like each other. They really want to stay together. They're really strongly attracted to each other. So not many separate. And as a result, you only have a few little hydrogens zipping around the container, so that produces a weak acid. So if you look at this picture, here's our hydrogen. Hydrogens are the little guys, H+. Here's our big anion. We could say this is chlorine with a -1. We could say it's fluorine. We could pretend that this, just an F there. We could pretend that this is sulfate with a -2. We could pretend it's any negative ion that normally is bonded to the H. But they all dissociate. They all separate from each other. So this produces a strong acid. Whereas over here, there's a lot of these guys that are still together. The H is the red, so it's still together, still together, still together, still together. You getting the idea here? Here's one set, here's two sets, and here's three sets that actually have separated. But there's an awful lot that are still together. So that means not many have dissociated, so it's a weak acid. If you look at these guys here, the HCl has separated. The little H pluses, they've separated from the Cl's, but yet you don't see any H pluses in here, but instead you see that hydronium ion. That hydronium ion is formed when you have H2O plus an extra H plus ion. So we end up with H3O with that +1 charge. And that's all these guys. So we could represent it as just an H, or we could represent it as H3O. Doesn't really matter, it's the same idea. But either way, you drop this in, and you see that it's a plus and a negative, plus and a negative, plus and a negative. They've all separated, so this is a very strong acid because it completely dissociates. This picture, you drop in the HF, and we still have HF, still have HF, still have HF. Only one set have separated. And you can see the visual over here. This is what it looks like out of the container. Put it in water, still have it, still have it, still have it. This is the only one that's separated, so this is a weak acid. Alright, part 3. So let's take a quick look at acetic acid. This is a very weak acid. When 1 mole is dissolved in water, 0.4 actually dissociates into hydrogen ions. That's not even 0.5%, never mind 1%. Only 0.4% of the acetic acid molecules will actually dissociate, separate into hydrogen ions and then the acetate ions. So that gives you an idea of how weak this really is, which gives us an indication of whether or not we can drink it or not. We're not going to be drinking something that dissociates into lots and lots of hydrogen ions because that's going to be a strong acid, whereas this one's going to be much weaker, not as many hydrogen ions zipping around in there. Same thing holds true for bases. Na and then the OH, you separate this, or this goes into solution and they separate. 1 separated, 2 separated, 3 separated. They all separated. Here's the purple is the Na, and then the OH is the red and the white. So you see that they've all separated. This is a strong base. NH3, remember we said it doesn't have the OH in it in the formula itself, but yet it produces the OH. But it's kind of a weak base here because you put NH3 in, you still have NH3, still have NH3, still. Only one set has actually donated that H and created, or in this case the NH3 has accepted the H from the water and created the OH ion. So this is a very weak base because most of them stay together just like it is when it's getting put into the container. Okay? Not many of them react. So you decide. Pause this for a sec, take a peek. Is this strong or weak? Alright, hopefully you decided that this is a weak acid because 1 stays together, 2, 3, and even 4 stay together. These two separate, and these two separate. You can tell they separate because you see the actual positive and negative charges. If they're still together, then the whole thing balances each other out. Positives cancel out the negatives, and it's neutral. What do you think? Strong or weak? Good. Hopefully you've decided they're all separated, so this is a strong acid. Alright, acidic versus basic solutions. Acidic solutions are going to have more H's than OH's, and basic or alkaline, new word here, contain more OH's than H's. Now, solutions always contain both ions, just not always in equal proportions. If they were equal, then you would have a neutral solution. Now, think about what H and OH is. Don't you have two H's here and one O? Isn't the formula for that H2O? That's water. So if you have, let's say, 5 moles of this, and then you have 5 moles of this, well, how many moles of water can you make? 5 moles. But what if you have 10 moles of hydrogen and only 4 moles of hydroxide? How many moles of water can you make? Well, the answer, I hope you got, is 4. You would use up the same amount of hydrogens and you would make 4 moles of water. But all this extra stuff, this 6 extra moles, that would be of hydrogen, so there would be an imbalance here. It wouldn't be nice and neutral because they're not even. You have more hydrogen, so this makes it acidic. The flip side, if you have more hydroxides than hydrogen, this makes it a basic solution. So whenever we're looking at pH, we're deciding if something's acidic or basic, we're always saying, is there an imbalance in the number of H's versus OH's, and how much, or to what extent is that imbalance? Is it just slightly, or is it a lot? The pH scale, these guys measure the actual concentration of hydrogen ions. Technically, it's the hydronium ions, but you could just think of it as the hydrogens, because the hydrogens combine with the water to make hydroniums. We're not going to get into too much about how the pH is calculated. You will do that at a later date if you take a more advanced chemistry class. But what you should know at this point is that it runs from 0 to 14, that 7 right in the middle here is neutral. And as you are moving out from the center, moving out from 7, you first hit the weak amounts. These guys are weak acids, weak bases, and then if you keep going, it gets stronger, stronger, stronger. Meaning if you go this way, towards the lower numbers, it gets strongly acidic. There's lots and lots and lots of hydrogens zipping around in the container versus over here where there weren't as many. And then the flip side, if you go out towards 14, it's very strong because there's lots of OHs zipping around. And over here with the weak basic, there weren't as many. So just remember, a lot of kids think for some reason that this is a strong acid. They do a real good job with that. They know that this is a weak acid. They know that this is neutral. But then they think we start all over again with this pattern, and they say that this is a strong base, and then as we go out, it's a weak base, and they follow the same pattern: strong acid, weak acid, strong base, weak base. This is not correct. Don't make that mistake. As you move away from neutral, it gets stronger, 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 and it's the strongest out here in the high numbers. All right, take a peek at some of the household items. One that I do want to point out that you should be familiar with, where's my pen, is that blood is slightly acidic. Slightly basic. Blood is slightly basic, and it needs to stay in that range. If it starts moving out of that range, then you're going to end up setting off all sorts of alarms in the body, and the body's going to do things to quickly rectify the situation and get the blood back into that basic range. We'll talk about that in a couple minutes. Notice gastric juices over here. Notice soda, not the best thing to be drinking, and so forth. Alright, like I said, if you take an advanced college or even math course and you start working with the log function, there's even a special calculator or button on your calculator that deals with this. But basically what it's showing you is that the pH is going to change with a power of 10. Let's take a look. This might not mean a whole lot to you. Let's take a look at the next slide.